Okay, here's a thought. What if everything we think we know, like everything, about life in the universe? What if it's based on just one example? Ours.
Mm-hmm.
Imagine alien life that doesn't need oxygen, doesn't drink water, isn't even, built from carbon atoms. Sounds like pure sci-fi.
It
Jump
really
into
does. But what's amazing is this isn't just science fiction anymore. It's becoming a serious field of scientific exploration.
Exactly. And that's why today we're doing a deep dive into this really fascinating world of, well, let's call it unearthly biochemistry.
Unearthly biochemistry, I like that.
Our mission, basically, is to explore the theories, the discoveries, the stuff that challenges our uh, carbon chauvinism,
That's the term, yeah.
and really open up the possibility of life forms that are just truly alien.
Mm.
We want to unpack what life might look like if it just broke all the rules we assume are fixed.
And to do that, we've pulled together insights from, well, quite a range of people: astrobiologists, chemists, planetary scientists.
The whole gamut.
Pretty much. We've got new research from Oxford on applying evolutionary theory to aliens, which is wild, discussions on alternative solvents, different chemical building blocks, and the latest findings from telescopes like JWST.
JWST always delivers something interesting.
Doesn't it? And we'll also look ahead at what the extremely large telescope, the ELT, might show us, plus some really cutting-edge work on, believe it or not, how life might have started on early Mars,
Okay.
and what that tells us about searching elsewhere.
So let's start with that bias. Carbon and water.
Hmm.
When I think alien, my brain defaults there. I mean, carbon makes these incredible long chains, right? DNA,
It's
proteins,
incredibly versatile, absolutely.
and water, well, it dissolves almost anything. It's made of common stuff.
Yeah.
Hydrogen and oxygen. Seems like the perfect setup.
Yeah,
But is that just us projecting? Is it cosmic bias?
that's the core of it. While carbon and water are, objectively excellent for the kind of life we know, assuming they're the only way life can happen in this vast universe, that might be, well, incredibly limiting. Carl Sagan famously called it carbon chauvinism.
Sagan.
Yeah, he really pushed back against the idea that life must look like us chemically. He argued our perspective is just too narrow, shaped only by Earth.
So if we manage to shake off that chauvinism, broaden our thinking,
Mm.
what else could actually be out there? We talked building blocks, but what about the liquid, the solvent? Water's our go-to, but what other cosmic liquids could host life's reactions?
Well, ammonia NH3 is a really strong contender.
Ammonia, like cleaning fluid ammonia.
Chemically, yes, though obviously we're talking pure ammonia in vast quantities. It's polar, like water, which is good for dissolving things, and nitrogen's super abundant in the cosmos.
Okay.
So it could be a solvent in really, really cold places. It freezes at about 195 Kelvin,
Which is?
minus 110 Fahrenheit, roughly. Much, much colder than water's freezing point of 32 Fahrenheit, or 288 Kelvin.
Wow. So that opens up a whole different temperature zone for life.
Exactly. It means potentially habitable environments on freezing cold exoplanets or moons, places like maybe Titan, although Titan has other liquids too.
Hang on, you mentioned something interesting earlier. Ammonia doesn't expand when it freezes, like water does.
That's right. Water ice floats because it expands and is less dense. Ammonia ice sinks.
So for life in an ammonia ocean, freezing might not mean being crushed or shattered by expanding ice.
Precisely. It might just mean things slow down or the organism has adaptations. It potentially makes the habitable temperature range wider. Ammonia is also good at holding heat.
Other downsides.
Oh, definitely. It boils at a lower temperature than water. It can be quite reactive. And UV radiation from stars can break down ammonia vapor pretty easily.
Oh.
Also, if water is present, ammonia just mixes with it completely. So getting pure ammonia oceans might be tricky in some spots.
Okay, ammonia is one thing,
Mm.
but you mentioned sulfuric acid. Seriously,
Yep. Sounds extreme, I know.
extremely extreme.
Yeah.
How could anything live in acid?
Well, believe it or not, it's actually been proposed as a potential habitat in the clouds of Venus.
Venus's clouds.
Yeah, they're mostly sulfuric acid, like 70 to 100%. Now,
Yeah.
obviously, Earth biochemistry would dissolve instantly.
Obviously.
But some studies suggest that certain types of silicon chemistry might actually be stable in concentrated sulfuric acid.
Silicon chemistry. Okay, we'll get back to silicon. But stable in acid.
It's definitely a mind bender. One challenge is viscosity sulfuric acid gets really thick as it gets colder, which would slow down reactions that depend on things diffusing around.
Right.
But you could still have energy sources, like sunlight for photosynthesis maybe, powering life, even if it runs at a, let's say, different metabolic speed.
Okay, so we've got extreme cold with ammonia, extreme acid.
Mm.
What about something less chemically aggressive? Like on Titan, Saturn's moon. It's got those famous lakes.
Right. Titan's lakes aren't water. They're liquid methane and ethane.
Hydrocarbons.
Exactly. Non-polar solvents. And they could potentially host really exotic biochemistries. NASA has actually kicked around ideas about life on Titan that might, say, metabolize hydrogen gas and acetylene, a completely different way of breathing and getting energy.
Wow.
And that's not even the weirdest. People have speculated about, like, liquid helium on super cold worlds, maybe hosting superconductors or natural computers.
Computers?
Highly speculative, of course. The chemistry would likely be incredibly slow. Or, at the other extreme, maybe even life in molten rock, silicate lava.
Whoa, okay, that's really out there.
High temperatures, SiO bonds constantly breaking and reforming. Very hard to imagine, but we're trying to break the mold here.
Okay, let's swing back to the building blocks then. We talked about the liquids. Carbon is king because it forms these long, complex chains, the backbone of everything we know. Can anything else really do that job?
Silicon. That's the most commonly suggested alternative.
Right. You mentioned silicon chemistry and acid.
Exactly. Silicon is right below carbon on the periodic table. It can also form 4 bonds, like carbon. And it's super abundant, especially in rocky planets' second most common element in Earth's crust after oxygen. People have been thinking about silicon life for ages, actually. Julius Scheiner back in 1891.
1891, wow.
Yeah. But there are big challenges. The bond between silicon and oxygen is incredibly strong. Think quartz, sand, silicon dioxide, rock, basically. So a silicon-based life form using oxygen for respiration, like we do. Well, the waste product wouldn't be CO2 gas. It would essentially breathe out sand or silica.
Breathe out sand. Okay, that's an image I won't forget.
It's pretty alien, isn't it? Also, silicon bonds aren't as stable as carbon bonds, especially when water or oxygen is around. Making complex silicon molecules often takes more energy, and they don't dissolve well in really cold solvents.
But there are upsides.
There are. Silicon compounds can handle much higher temperatures than most carbon ones.
Yeah.
So maybe life on scorching hot planets near volcanoes, deep-sea vents, that's where silicon might have an edge. And it's interesting, life on Earth already uses silicon, just not usually as the primary backbone. Diatoms build glassy shells from silica. Some plants use it for structure. Sponges have silica spicules. Even we use it a tiny bit in bone formation.
Right.
And on some hypothetical planets called carbon planets, where carbon is way more abundant than oxygen, maybe you could get weird silicon-carbon hybrid life forms. Hese bonds.
A mix and match biochemistry.
Perhaps. And it's not just silicon. Arsenic has been floated as a possible substitute for phosphorus in DNA-like molecules.
Arsenic. Isn't that poison?
To us, absolutely. Highly toxic, messes with our phosphorus-based chemistry. And arsenic compounds tend to be less stable than phosphorus ones in water. But could a different biochemistry evolve to use it? It's speculative.
And this goes beyond just swapping elements, right? You mentioned different molecules carrying the genetic code.
Exactly. This is really cool. Scientists have actually created synthetic molecules in the lab called xenonucleic acids, XNA. Yeah. Like HNA, hexadenal nucleic acid, is one example. These are chemically different from DNA and RNA, different sugars, different backbones sometimes, but they can do the same job. They can store genetic information and even evolve in the lab.
So alien life might not have DNA or RNA at all, but something totally different doing the same thing.
It's entirely possible, which means its genetics, its heredity could work in ways we haven't even conceived of yet. And, if we link this back to real observations, think about that dimethyl sulfide, DMS, signal the JWST might have detected on K2-18b.
Ah, yes, the potential biosignature.
Right. On Earth, DMS is overwhelmingly produced by life, mostly marine microbes. Now, the detection is still tentative. It's at what scientists call 3 sigma, meaning there's still a possibility, about 0.3%, that it's just random noise or some other chemical mimicking the signal. They really want to get to 5 sigma for a confident detection.
Which is much more certain.
Much more. Like a 1 in 3.5 million chance of being wrong. But if it holds up, finding DMS there suggests life might pop up fairly easily when conditions allow. And it might produce chemicals we weren't necessarily expecting to find as the primary sign.
Okay, so we've journeyed through this cosmic chemistry lab. Silicon life breathing sand, ammonia oceans, acid clouds, XNA genetics. It's all pretty mind-bending. But does this mean life, no matter how weird its chemistry, still follows some basic rules, like universal laws?
That's a really fundamental question, and some fascinating new research, particularly out of the University of Oxford, suggests the answer is probably yes.
Okay.
The idea is that aliens, no matter their makeup, carbon, silicon, DNA, XNA, whatever, are likely shaped by the same core process that shaped us, natural selection.
Evolution.
Exactly. Evolutionary theory, they argue, can actually be used to make predictions about alien life, about its complexity, maybe even its behavior, without knowing the specific chemical details. Well, think about how complexity arose on Earth. It happened through what biologists call major transitions, like single cells clumping together to become multicellular organisms.
Sort of simple to complex.
These transitions often happen under extreme pressure or when cooperation provides a huge advantage. The theory suggests alien life would likely also evolve complexity through similar transitions, forming hierarchies of entities working together, like cells in a body or individuals in a society. They'd need mechanisms to manage conflict within the group, just like we do.
So even silicon aliens might have, like, societies or multicellular forms driven by evolutionary pressures.
It's plausible. The underlying principles of adaptation and selection could be universal, even if the biological hardware is completely different.
Okay, so that's the micro level, evolution. What about the macro? Whole alien ecosystems, are there rules for how those might work?
Yeah, absolutely. Astrobiologists and ecologists are thinking about this too. There seem to be some general ecological principles that should apply anywhere life exists. Let's call them principles of exoecology.
Exoecology. Okay, like what?
Well, first, environmental interaction. Life adapts to its environment, sure, but life also changes its environment.
Like how early life on Earth produced oxygen and changed the whole atmosphere.
Precisely. It's a two-way street everywhere. Second, ecosystem design. Any ecosystem needs energy coming in, ways to recycle materials, think producers, consumers, decomposers, and usually organizes into a hierarchy, like a food web. Interestingly, Earth's food webs rarely have more than 4 or 5 main levels or trophic levels.
So probably no super complex 10-step alien food chains then. There's an efficiency limit.
Seems likely, yeah. Energy transfer is inefficient, which leads to the third point. Ecosystem dynamics. Energy flow decreases as you go up the food chain. Generally, more available energy means more biodiversity, and energy always gets converted to heat, eventually basic thermodynamics.
Okay, makes sense.
Fourth, material cycling. Stuff has to be reused. Elements cycle through the system. If key elements cycle as gases, they tend to get distributed evenly. If they're solids or liquids, you get patchier distribution. And the availability of certain materials can limit how much life the system can support.
So an alien planet might be limited by its version of nitrogen or phosphorus cycling, just like on Earth.
Could be. And finally, fifth, temporal cycles. Ecosystems change over time due to external things like day-night cycles, seasons, maybe stellar flares, and also internal dynamics. Stable ecosystems often have one main thing limiting growth at any given time.
So even alien worlds would have their rhythms, their cycles affecting life.
Almost certainly. So yeah, even if the life itself is utterly bizarre chemically, these ecological principles give us a kind of framework, a way to predict how it might function as a system.
You mentioned energy input for ecosystems. Sunlight is the obvious one for us, but what else could power life out there, especially in weird places?
Oh, loads of possibilities beyond just starlight. Geothermal energy is a big one. Think volcanic activity, like on Jupiter's moon Io, which is incredibly volcanic.
Right.
Or tidal forces. Jupiter's gravity constantly squeezes and flexes its moon Europa, generating heat that likely keeps its subsurface ocean liquid.
Tidal heating, yeah.
Saturn's moon Enceladus is similar. It has geysers spewing water, ice, and gas into space from its ocean. And get this, NASA's Cassini probe found hydrogen cyanide in those plumes.
Hydrogen cyanide. Sounds nasty.
To us, maybe, but chemically it's incredibly useful. It's like a Swiss Army knife for building amino acids, the building blocks of proteins. The chemistry in Enceladus's ocean could potentially provide as much energy, researchers calculated, as a car battery.
A car battery's worth of energy from a moon's ocean chemistry. That's wow.
It really shifts the goalposts for where life could get its power. Then there's electricity itself. Imagine life on a planet racked by constant massive lightning storms. Maybe life evolves to harness that electrical energy directly, like natural lightning rods or even biological computers.
Okay, that's cool.
And then maybe even nuclear energy. Some radioactive isotopes decay over long periods. Could life use that? Maybe natural underground fission reactors, like the one that existed on ancient Earth in Gabon, or organisms incorporating something like carbon-14, using its decay like tiny internal diamond batteries.
Yeah, I'm in batteries.
Okay.
That life might be short-lived or need really rapid mutation and repair mechanisms, but it's theoretically possible. And the most out there idea, maybe even life based in high-energy plasma like inside a star's atmosphere. Purely hypothetical, of course.
Plasma life. Okay, my brain hurts a little now, but it really opens up the possibilities. So, with all this potential weirdness, how on Earth or off Earth do we actually find it if it's not breathing oxygen or using water?
That's the million-dollar question, isn't it?
Yeah.
The key shift in thinking is to move beyond just looking for Earth-like biosignatures. We need to look for signs of non-equilibrium chemistry.
Non-equilibrium,
And-
meaning chemistry that shouldn't be happening on its own? Systems that are actively using energy to build complex stuff, to maintain a state far from chemical balance. Life does that. It fights against entropy. So we look for weird chemical mixes, unexpected gases in atmospheres, things that hint at an active process, regardless of whether it's based on carbon and water. And we need to look everywhere, including those extreme environments where our kind of life just couldn't make it.
And we're building new tools to do just that,
Right.
right? These giant new telescopes. Tell us about the ELT.
Right. The extremely large telescope. It's under construction in Chile, aiming for first light around 2029 or 2030. And it is extremely large. The main mirror will be 39 meters across.
39 meters. It's enormous.
It's huge. It'll collect an unprecedented amount of light. The big advantage is it'll be able to analyze the atmospheres of exoplanets, even Earth-sized ones around nearby stars, in just a matter of hours.
Hours. Really?
Yeah. And crucially, its instruments are being designed specifically to help distinguish between chemical signals that could be produced by life biological versus those from just geology or atmospheric chemistry, inorganic. The potential is staggering. Some projections suggest it could detect signs of life on a planet like Proxima b, if they exist, in maybe just 10 hours of observation time.
10 hours. That's incredible. And we've already got JWST up there giving us hints.
Exactly. The James Webb Space Telescope is already a game changer. We talked about the potential DMS signal on K2-18b.
The potential life gas.
Potential, yes. Still needs confirmation, that 5 sigma level of certainty. But just the fact that JWST can even detect trace gases like that in an exoplanet atmosphere hundreds of light years away is revolutionary.
Yeah.
If that DMS signal or others like it are confirmed, it really would suggest that life might be common, popping up wherever conditions allow, even if its chemical outputs are a bit surprising to us.
So this wider view of life, does it also change how we look closer to home? Like Mars. We always talk about following the water.
It does. The thinking is shifting a bit. Instead of just looking for habitable environments, places with liquid water, basically some scientists argue we should be looking for urable environments.
Durable. What's that?
It's from the German meaning primitive or original. An urable environment is one that's dynamic, complex, maybe even a bit harsh. A place that doesn't just allow life to exist, but actively drives the origin of life, where challenges force innovation, chemically speaking,
Okay.
like volcanic hot springs. They have chemical gradients, energy sources, wet-dry cycles, lots of action. And we know early Mars likely had plenty of those.
Ah, so not just a calm pond, but somewhere with more chemical drama.
Exactly. And recent research looking at early Mars's specific geochemistry is fascinating. Mars had a lot more iron around than early Earth. Experiments suggest this high iron content might have been tough for the very first primitive cell membranes to handle a selective hurdle.
Makes sense. Iron can be reactive.
But maybe it was also an evolutionary advantage. Those protocells that could cope with iron might have been pushed towards greater stability or different structures. For instance, tests show iron ions, Fe2+, disrupt simple fatty acid membranes less than calcium ions do, but more than magnesium ions. And things like acidic water actually reduce the disruption. Membranes made of mixed types of fatty acids are more stable. And if RNA, a candidate for early genetic material, interacts with these membranes during wet-dry cycles, it helps them hold together better.
So the specific Martian chemistry could have pushed any emerging life down a slightly different path right from the start.
Precisely. It suggests Martian life, if it ever arose, might have had unique adaptations baked in from day one due to its environment. So the search strategy follows. We should be intensely focusing on those ancient hot spring deposits on Mars. Life might have started there. And if surface conditions got too harsh later, maybe it retreated underground through the plumbing of those hydrothermal systems. It might still be there, deep down.
Waiting for us. Okay, so wrapping this up. We've really journeyed far beyond Earth, haven't we?
We really have. We've seen how life might ditch carbon and water, maybe use silicon or arsenic, swim in ammonia or even acid, encode its genes in something like XNA, and draw power from lightning or radioactivity. It's a huge expansion of possibilities.
But even with all that potential weirdness, those universal rules, evolution, ecology, they probably still apply, giving us a way to think about how truly alien life might work.
That seems to be the emerging consensus, yeah. A framework for the alien.
The universe is just incredibly vast, chemically diverse,
Right.
way more creative than we probably imagined. And as we get these powerful new telescopes online, refine how we search, the big question isn't just if there's life out there anymore, is it?
No, I think it's shifting towards how diverse, how mind-bendingly unexpected could it be.
Yeah.
And maybe here's a final thought to chew on. If the origin of life isn't about finding a nice, calm cradle, but about environments that actively break things, membranes, molecules, and force them to make themselves stronger, more complex, through selection.
The arable idea.
Exactly. Then maybe the most promising places to look for aliens aren't the gentle, Earth-like worlds we dream of. Maybe it's the most geochemically challenging, dynamic, seemingly hostile planets out there. What kind of breaking and making might be happening right now on some distant, turbulent world, forging life beyond anything we can currently conceive?